In Questa, 60% of the adults travel to work by car. Part A, in a random sample of 12 adults, find the probability that the number who travel to work by car is less than 10. So N here is 12 and the probability of success is 0.6. If X is the number of adults who travel to work by car out of a sample of 12, then X follows a binomial distribution with N equals 12 and P equals 0.6. To find the probability that the number who travel to work by car is less than 10, we find the probability that X is less than 10. And we use the complement rule here. Probability X less than 10 plus probability X greater than or equals to 10 is 1. So upon rearranging probability that X is less than 10, this is 1 minus probability X greater than or equals to 10, which is 1 minus probability X equals 10 minus probability X equals 11 minus probability X equals 12. In total, there are 12. And probability X equals 10, that will be 12C10, 0.6 to the 10, 0.4 to the 2. Probability X equals 11 is 12C11, 0.6 to the 11, 0.4 to the 1, and probability X equals 12 is 12C12, 0.6 to the 12, 0.4 to the 0. So when we evaluate this, we have 1 minus. All these are evaluated to 5 significant figures for accuracy. We have 0.06385 2, 0.017414, and 0.0021768, which is 0.917. Part B, a random sample of 150 is taken, and now is much larger at 150. P is 0.6. So when N is large and P is 0.6, we cannot just use the binomial distribution. We want to find the probability that the number who travel to work by car is less than 81. So less than 81, yeah, we are not using a binomial for that. So we need to use an approximation. When N is large and P is close to 0.5, we approximate it by a normal distribution. We have to find the mean and the variance of the normal distribution. So let's say over here, we have X follows a binomial distribution with N equals 150 and probability of success is 0.6. And for this case, to find the mean for the approximation, mean is always given by NP. So we have 150 times 0.6, and that is 90. The variance is NPQ. We have 150 times 0.6 times 0.4, and that is 36. So Y here follows a normal distribution with a mean of 90 and a variance of 36. We want to find the probability that X is less than 81. So we have to apply the approximation. We use a continuity correction from a binomial, which is a discrete to a continuous normal distribution. we must apply the continuity correction factor. So probability x less than 81 is the same as probability y less than 81 minus 0.5. So that will be 80.5. And then we standardize. So we have 80.5 minus the mean divided by the standard deviation. Variance is 36, standard deviation is the square root of variance, which is 6. And this is the probability that Z is less than negative 1.5833. Probability Z less than negative 1.5833. We have negative 1.58 here. This is the area that we want, but you won't be able to find this area in the normal table that is given to you. So instead, you work with 1.5833. We need this area. We can find this area from the table. From the table, this is 0.9433. And this area that we want is 1 minus 0.9433. We have 0.0567. That is for part B. Part C, justify the use of your approximation. In order to approximate to a normal distribution, we have conditioned that NP and NQ must both be greater than or equals to 5. NP is the mean, which is 90. This is greater than or equals to 5. In fact, it's greater than 5. NQ is 150 times 0.4, which is 60, and this is greater than 5. Since both NP and NQ are greater than 5, we can use the normal approximation to the binomial to compute the probability in part B.